Okay, so before we start the lecture, let's watch the pre-recorded video, and then I will explain the videos with the slides after that. Okay.
Assalamualaikum and a very good day. So today we are going to cover chapter 27, which is quantum physics. These are all the subtopics that we are going to learn from this chapter 27. This chapter basically 27 is from your textbook or reference book. So we're going to look into 27.1, blackbody radiation and Planck's hypothesis, and then point 2, photoelectric effect and the particle theory of light. And then we skip point 3 and point 4 from your textbook, and we straight go to the point 5, the Compton effect, and finally point 6, the dual nature of light and matter. So in this lecture, I'm going to brief you on 27.1 and point 2 only. After completing this chapter, we expect the students should be able to: the first one, define blackbody radiation and explain Wern's displacement law, Planck's quantum hypothesis of quantized energy, and then define photons and its properties, describe photoelectric effect, discuss non-classical features of photoelectric effect and their explanations using photon theory of light, and then apply photoelectric effect equation to quantum systems, define momentum of a photon in relation with the quantum energy, describe briefly on Compton effect in terms of conservation of energy and momentum, state the de Broglie's hypothesis and explain the dual nature of light and matter, and finally apply de Broglie wavelength of particle formula. Before we begin, let's go through a brief introduction on quantum physics. It is mentioned here attempts to explain behavior of matter on the atomic level if the laws of classical physics were unsuccessful. Meaning that if you try to explain behavior of, say, for example, electron using classical physics, these classical physics are those that you learn during the first semester. So you try to explain the behavior of this electron using what you have learned during the first semester. It is mentioned that the attempts is going to be unsuccessful. So various phenomena such as the electromagnetic radiation emitted by heated object, for example, couldn't be understood within the framework of classical physics. Meaning that if you look at this graph, this is a graph showing that electromagnetic radiation emitted by heated object, meaning that if you hit an object, say you have a ball, and if you hit the ball will gives off radiation. And if you try to plot the relative intensity of the radiation versus the frequency, according to the old classical physics theory, what you are going to get is this blue line. This blue line. This is what we expect to happen if you are using the theory of classical physics. Somehow, experimentally, this is not the case. You are not going to get this blue line here, but experiment shows that what you are going to get is this curve. So in other words, we can say that the classical prediction or the classical physics fails in this experiment, meaning that you need a new theory to explain the new spectrum that you have here. So around 1930s, a modern version of mechanics called quantum mechanics was highly successful in explaining the behavior of atoms, molecules, and nuclei. Meaning that this new theory called quantum mechanics is able to explain this curve, this experimental observation. Now let's look at 27.1, blackbody radiation and Planck's hypothesis. An object at any temperature emits electromagnetic radiation called thermal radiation. Meaning that, say if you have, example, a ball, any object, for example this ball, emits electromagnetic radiation called thermal radiation. Somehow, probably you cannot see the radiation. Why? because it falls not within the visible spectrum, whereby your eyes are sensitive enough to see the radiation. It could be infrared, it could be ultraviolet, for example. So any object, it doesn't matter whether it's cold or it's hot, all of them emit these thermal radiations. That is why it is mentioned here, an object at any temperature emits electromagnetic radiation called thermal radiation. And then the spectrum of radiation depends on temperature and properties of the object. So if you try to plot, if you can capture, say for example, you have a device, for example, and this device can capture the intensity of this outcoming radiation and also the wavelength. Now, if you plot the radiation versus the wavelength, you can get this spectrum. So this spectrum, the spectrum of radiation, depends on temperature and also the properties of the object. So for example, if you look at this graph, the temperature is 5000 Kelvin, meaning that this graph is if the temperature is 5000 Kelvin, and then the spectrum depends on, it's mentioned here, the spectrum depends on temperature, meaning that, say for example, you reduce the temperature to 4000 Kelvin here. So you're going to preserve the shape of the curve. The shape of the curve remains the same. The only difference is that this peak will shift to the right here. And then if you use 3000 Kelvin, the peak is shifted even more to the right, and for 2000 Kelvin, it is shifted again to the right. But the shape remains the same, only the peak is going to shift. A careful study of thermal radiation shows that it consists of a continuous distribution of wavelength from UV, visible, and IR. Meaning that if you look at this curve, so if you look at this curve, you'll notice that it consists of ultraviolet portion here, and then visible light here, and also infrared here. So it consists of wavelength from UV, visible, and infrared. At low temperature, however, the wavelengths of the thermal radiation are mainly in the infrared region. So, for example, if you look at this graph, the 2000 Kelvin, you'll notice that the graph falls within this infrared region only here, only within this infrared region, whereby the peak is also in this infrared region. You don't have this visible and also ultraviolet portion whenever the temperature goes low. So at low temperature, wavelengths of the thermal radiation are mainly in the infrared region. An ideal black body absorbs all the light that is incident upon it. A black body is a theoretical object that absorbs 100% of the radiation that hits it. Therefore, it reflects no radiation and appears perfectly black. So thing is this way, how do light interacts with matter? For example, you have a ball, and then you hit the ball with radiation. So the light could be absorbed by the ball, or part of the light could be reflected by the ball, and some portion of the light could be passed through or transmitted through the ball. So there are three things could happen when light interacts with matter. It can be absorbed, it can be reflected, or it can be transmitted. So we come across this idea of black body, whereby this black body is what? It's a theoretical object that absorbs 100% of radiation that hits it. Meaning that if your ball somehow absorbs all the light incident on it, whereby no reflected light and no transmitted light, now you can treat your ball as a black body. So black body again is a theoretical object that absorbs 100% of radiation that hits it. Therefore, it reflects no radiation and appears perfectly black. An ideal black body is not just an ideal absorber whereby it absorbs 100% of light. It is also uh, an ideal radiator, meaning that it can radiate 100% of radiation. So if you measure the intensity of the electromagnetic radiation emitted by ideal black body, you will find this graph that we have seen previously. So this is the shape of black body radiation. Now, if you look carefully on the graph, you'll see that this temperature is 12,000 Kelvin and here is 6,000 Kelvin. And you can see that the peak shifts to the left. But in the previous graph, we have seen that the peak shifts to the right. Thing is this way. Here we plot the x-axis using frequency. And on the previous graph, on the previous slide, we plot the x-axis using wavelength. So if we plot x-axis using frequency, at lower temperature, the peak shift to the left. But if you plot the x-axis using wavelength, you'll see that the peak shift to the right. The distribution of energy in black body radiation is independent of the material from which the black body is constructed. So the distribution of energy depends only on the temperature. And the peak frequency is given by this equation, meaning that to relate the previous graph, we have peak frequency here, and this peak frequency actually depends on the temperature of the object. The peak wavelength increases linearly with the temperature, and according to the previous equation, the Wier's displacement law, this means that the temperature of a black body can be determined by its color. So if you refer to the previous equation whereby F maximum or F peak equals to some constant multiplied by T, whereby this equation shows that the peak frequency changes according to temperature, hence you have the shift to the left or to the right of the peak. If you change this equation, you change this frequency in terms of lambda. Now you can write the equation as lambda max multiplied by temperature equals to some constant which has this value 0.2898 multiplied by 10 minus 2. So this is also Wier's displacement law equation. You just change the equation from F, now you're using lambda. And coming back to this statement, this means that the temperature of black body can be determined by its color. So meaning that certain color has certain frequency. For example, for blue color, the frequency, not frequency, wavelength. The wavelength is 450 nanometer. So whenever you have blue radiation, blue color here, the wavelength is 450 nanometer. And if you input this value inside this equation for the lambda, the wavelength, now you can calculate or predict what is the temperature. So that is what is meant here. This means that the temperature, which is this, of a black body can be determined by its color. So for blue, it is 450 nanometer. Classical physics calculation were completely unable to produce this temperature dependence, leading to something called ultraviolet catastrophe. So this is what I mentioned earlier, that the classical physics predict this graph, but experimentally, this is what you got. So only quantum mechanics can explain this behavior or this observation. A wood fire at 1500 Kelvin puts out peak radiation at about 2000 nanometer. 90% of its radiation is at wavelength longer than 1000 nanometer and only a tiny portion at visible wavelength. So consequently, a campfire can keep one warm, but it's a poor source of visible light. So now you can refer to this, say, graph. So it says it is 1500 Kelvin, which is close enough to this 2000 Kelvin. So 90% of its radiation is at wavelength longer than 1000 nanometer. So this is 1000 nanometer. So 98% say for example, we treat this curve as 1500 Kelvin. So 90%, which is all this portion, so 98%, sorry, 98, not 90, 98% of its radiation is at wavelength longer than 1000 here, and only tiny portion somewhere here at visible wavelength, which is between 390 to 700 nanometer. So that's why consequently a campfire can keep one warm, but it's a poor source of visible light because it only crosses a tiny portion of visible light. This is another example. Effective temperature of sun is 5778 Kelvin. Using Wien's law, one finds a peak emission per nanometer of wavelength at a wavelength about 500 nanometer in the green portion of the spectrum near the peak sensitivity of human eye. So this is close enough to this 5000 curve, whereby even it is 5778 Kelvin, now you can approximate using this 5000 K curve. So using Wien's displacement law, you find the peak is around 500 nanometer, so which is somewhere around here, which is about 500 nanometer, and this 500 nanometer is in the green portion of the spectrum, so it's somewhere near to the green color here. A scientist named Planck, he discovered that he could reproduce the experimental curve by assuming that the radiation in a black body came in quantized energy packets depending on the frequency, whereby this is the equation. In other words, this guy named Planck, he discovered that the experimental curve, this curve that we have seen before, he can reproduce this curve only if he treat that radiation in black body came in quantized energy packets depending on frequency, meaning that he came up with this equation whereby En equals to NHF, where E is the energy and N is from 0, 1, 2, 3, and so on. H is called the Planck constant, where the value is given here, and F is the frequency. So what is significant about this equation is that this equation states that the energy depends on frequency. Now, say for example, you have a black body, and this black body gives off radiation. Now, let's say the radiation given off has this curve whereby the peak frequency or the peak wavelength is at 450 nanometer, which is the blue light. Now you can always change the lambda later on to frequency by using V equals to F lambda, this equation, to change this 450 nanometer to frequency. So now knowing the frequency, the peak frequency coming out from this black body radiation, if you input the value of frequency here into this equation, now you can calculate how much energy being given off by this black body. This is solar radiation spectrum. So our sun is a good approximation for black body radiation. So if you look at our sun and you capture the radiation coming off from the sun, you can see the plot replicates the black body radiation here. So it's similar to black body radiation, except for some part whereby you notice some of the wavelength. Let's say for example, this portion is missing, and also this portion is missing due to absorption of the light, meaning that the light, this is radiation at sea level. So the sun is here, and there are many other things in the atmosphere before it can reach sea level. So this is sea level, for example. some portion of the radiation might be absorbed by the cloud. So you have many cloud, then there are many more absorption of the radiation. So that is why this portion is not visible at sea level, because this portion now is being absorbed by the water molecule. If you look at this portion, the UV wavelength, so sunlight at top of atmosphere, it consists of this UV portion. But after reaching sea level, you see that this portion of UV is now being absorbed by the ozone layer. Now let's move to the next subtopic, which is 27.2, the photoelectric effect and the particle theory of light. Einstein got his Nobel Award due to this experiment on photoelectric effect. And Einstein suggested that light comes in bundles of energy called photons that obey Planck's hypothesis of energy quantization. That is, light of frequency f consists of photon with energy given by this equation. Thus, the energy in a beam of light of frequency f can have only the values of hf, 2hf, 3hf, and so on. So in other words, according to Einstein, he treated light as made up of particles. So light is made up of particles, and that particle is called photons. And each photon obeys Planck hypothesis of this energy quantization, whereby energy of this photon is given by E equals to hf, meaning that the energy of the photons depends on the frequency, and each frequency reflects certain color. For example, now if you change this equation, E equals to hf, and you change f into lambda, whereby V equals to f lambda. Now f equals to V over lambda. So you input this into this, you'll get the energy equals to hv over lambda. Now this is another equation, E equals to hv over lambda. Now, according to Einstein, this particle of light again is made up of this photon, and this photon has energy depends on frequency or depends on the wavelength lambda. Meaning that, for example, if you have a blue light, whereby the blue light is made up of photons, which has wavelength 450 nanometer. So the blue light is 450 nanometer. You can input this value here and calculate what is the energy. In other words, say for example, green radiation has certain energy, blue radiation has certain energy, and red radiation has certain energy. And if you try to compare this to a fire, whereby we know that when the fire has a blue color, it's very hot compared to, for example, yellow. Why? Because blue has wavelength 450 nanometer, whereby for yellow it's around nearly 600 nanometer. So for yellow it's about 600 nanometer. So whenever the fire is yellow in color, the wavelength is 600 nanometer. But for blue, it is 400 nanometer, 450 nanometer. So wavelength of blue is lower compared to yellow. So when the wavelength is lower here, the energy is higher. So that is why the blue color fire has, it's hotter compared to yellow fire. So energy quantization means that the frequency can only have this value, hf, 2hf, 3hf, and so on. but it cannot take something in between, say for example 1.5 HF. So this energy does not exist. So that is what is meant by quantization of energy. Energy is quantized. In instant photon model, a beam of light can be thought of as a beam of particles, each carrying the energy hf as given previously. So if the beam of light is made more intense while keeping the frequency the same, the result is that the photons in the beam are more tightly packed so that more photons pass a given point in a given time, as shown in this figure. So high intensity light beam as compared to the low intensity light beam. So in this way, more photons shine a given surface in a given time, increasing the energy delivered to the surface per time. The photoelectric effect, this is where Einstein got his Nobel Prize, occurs when a beam of light strikes a metal and electrons are ejected. If you look at this experimental setup, you will notice that there is battery and there is emitter to read the current value, and there is emitter and collector here. But there is no wire connecting collector to emitter. So by there is no way current to flow because there is no wire to connect collector to emitter. So let me erase this. But when Einstein did this experiment, whereby he shines light onto this emitter, somehow the emitter is registering the value of current, meaning that even there is no wire connecting emitter to collector, somehow the emitter notices that current is flowing. So how come that things happen? So this is due to this what is called photoelectric effect, whereby when a beam of light strikes a metal, electrons are ejected. In other words, this light coming and hit this emitter. So this light coming by giving energy HF, we know that light consists of photon and that photon has energy HF. So this photon carries energy. It hits the emitter. When it hits the emitter, electrons from the emitter is jumping out to the collector. Then electron continues its motion to complete the circuit and to register the value of current in the emitter. It is mentioned here, each metal has minimum amount of energy required to eject an electron, called the work function. So if the electron is given an energy E by the beam of light, its maximum kinetic energy is given by this equation. So think this way. So for example, this photon, we know that it has photon has energy given by E is equals to HF. Now to simplify these things, let's say I just take a random value. Let's say the energy of this photon is 20, for example. And when this energy from photon, which is 20, hits the emitter, in order for electron to jump, it needs to overcome some value, which is called work function, to eject the electron. Meaning that, let's say the work function of the emitter is 10, for example. Now you supply 20, but energy required to eject electron is 10. So meaning that 20 minus 10, the balance is another 10. So that balance, another 10, becomes the kinetic energy of the electron. So again, you supply 20, for example. This is just some random value, by the way. And then to eject an electron, the work function is 10. So you required 10 to eject the electron. So 20 minus 10, the remaining is 10. So this 10 becomes the maximum kinetic energy. So that is what is meant by this equation. So Kmax, which is this uh, 10, is the balance energy. This E is the 20, and this W naught is the work function. According to classical prediction, the classical physics, any beam of light of any color can eject electron if it is intense enough. Meaning that to eject the electron, what you need is an intense light. You need an intense light according to the classical prediction. But somehow, this is not true, because according to quantum mechanics, light must have certain minimum frequency in order to eject electron, because each frequency has certain value of energy. And then the maximum kinetic energy of an ejected electron should increase as the intensity increases. And we know this is also not true, but more intensity results in more electrons of the same energy. So this observation is in accordance to the quantum mechanics theory, whereby if we treat this according to classical theory, it's going to fail. Here is the explanation. Each photon's energy is determined by its frequency, as I mentioned before, E equals to hf. If it is less than the work function, electron will not be ejected no matter how intense the beam. For example, let's say your energy in the previous example given is 20, right? In the previous example. And the work function that I gave earlier is 10. So now let's say the work function is 30, sorry. So the energy of the photon is less than the work function. So no matter how intense the beam you made, electrons will not be ejected. An electron is ejected only if an incoming photon has an energy at least equal to work function E equals to hf naught equals to W naught. So this is the cutoff frequency to calculate the minimum frequency to eject an electron. So the cutoff frequency is given by WO, the work function, divided by the Planck constant h. Now let's look at this example. A beam of light, a white light, containing frequencies between 4 times 10 power 14 to 7.9 10 power 14 Hz, incident on sodium surface, which has work function 2.28 electron volt. So the sodium, the work function is 2.28 electron volt. So question is asking what is the range of frequencies in this beam of light for which electrons are ejected from the sodium surface. So meaning that you have to calculate the cutoff frequency as given by the previous equation, which is F naught equals to W over H. And then the work function given is 2.28 EV, which is this. You need to convert into joule. So this is the conversion to convert electron volt to joule, and then divided by the Planck constant h. So the cutoff frequency is 5.5 10 power 14. Somehow you supply 4 to 7.9 Hz, right? So you supply 4 to 7.9, but the cutoff frequency only start from 5.5. So meaning that those starting from 5.5 to 7.9 is going to eject electron. Those below 5.5, meaning that 4 to 5.5 to below 5.5 is not going to eject the electron. So that answers the first question. Now let's look at B. Find the maximum kinetic energy of the photoelectrons that are ejected from the surface. So this is basically using the equation, this K max equals to E minus W naught. So you can change the E. Now you can change this E into HF, the energy of photon. So H is the Planck constant, which is this, and the frequency, maximum frequency 7.9. So you input the frequency here, minus the work function. So the work function given is 2.28 electron volt. Again, you have to convert into joule, and finally you can calculate what is the maximum kinetic energy, which is given here.
Okay, so that will be the pre-recorded video. So right now I will try to explain to you. Okay, so the topic is the for unit. Okay, so the main things in chapter 27 is for quantum physics. So, okay, we will learn, okay, chapter 27.1 and 27.2 up until today. Okay, and we will continue the rest of the chapter tomorrow. Okay, the black body radiations and the Planck's hypothesis, and lastly the photoelectric effects for today. Okay, so the one that have calculations will be the photoelectric effects here. So you must consider these things. Okay, should be your priority. But for your understanding, you also need to know or to study about the black body radiations. Okay, so first of all, you need to differentiate between the classical and also the quantum physics. Okay, what we learn in our semester one, okay, about motions, about force, is all about classical physics. And at to explain the behavior of matter on the atomic level, okay, so the attempts to explain the behavior of the atomic level in terms of atomic level using the classical physics theory will be unsuccessful. Okay, so classical physics will lead to the unsuccessful, whereby you should know to overcome this problem. Okay, so this line will be occur during the experimental observation around 1930s using the quantum, okay, quantum physics. So what is quantum physics? It is also known as modern physics. Okay, new approach in learning physics. Okay, to to overcome the problems having by the classical physics. So various phenomena such as electromagnetic radiations emitted by a heated object couldn't be understood. So the classical prediction on this part, okay, when you, let's say you have a material or you have a matter, okay, let's say the ball, and you heat up, and of course this ball is also radiates the electromagnetic radiations, and we expect that, okay, for the classical prediction will predict, okay, will predict when the intensity against frequency, it will be the intensity directly proportional to the frequency for the classical predictions. But in the experimental observation, it's not like that. Okay, it's having the a graph of curve like this. Okay, so at the very first part is the black body radiations, which you already learned in the videos about how can things or how can the spectrum of radiations from the object that have a different temperature. Okay, a spectrum radiations from object that have any temperatures which emits the radiation, EM radiations, which we call also the thermal radiations, right? And the spectrum, this spectrum of radiations, this one is spectrum of radiation, or in the plot of graph, it should be like this one, okay? The spectrum of radiations will depends on the temperature. And you look here, from 5,000, 4,000, 3,000, and 2,000 Kelvin. Okay, a careful study of thermal radiation shows that it consists of continuous distribution. So this spectrum, okay, is in the three different region, which is the ultraviolet, here, region A, region B is the visible range, and region C is the in the infrared. Most of the spectrum is on the infrared region. Okay, only a small portion is on the visible range, but that according to the temperature. If the temperature is the higher the temperature, we'll see a lot more in the visible range. And at low temperature, you can see at low temperature, for example, 2000s, okay, most of the spectrum is on the infrared region. Okay, most of the spectrum, just a few portions, okay, a very small portions for 2000 Kelvin is on the visible range region. Okay, right? So this is the black body, that the theoretical black body, theoretical object that absorbs 100% of the radiation that hits it. Therefore, it reflects no radiation and appears to be black, because when we have one matter, okay, and okay, sometimes the matter will transmit it, okay, transmitted, and sometimes, okay, the possibility of the radiation will be reflected, and sometimes, okay, radiation will be absorbed. Okay, so that when the 100% radiation absorb light, then we call that as the ideal black body. Okay, an ideal black body also an ideal radiator when it also give radiations like this one. Okay, following this graph. Okay, so this is the Wien's displacement law, where in this kind of equations, given that, okay, from our observations about the curve, okay, of intensity against frequency, we can see that, okay, at the peak of the curve, okay, this is the Wien's displacement law, so this is the peak of the frequency, and the frequency will depend on the temperature. All right. So sometimes they will ask about the ultraviolet catastrophe. So what is ultraviolet catastrophe? The classical physics calculations. Okay, this is the ultraviolet catastrophe. So when you try to explain this one, okay, please, okay, put this kind of graph, okay, to explain. So the classical prediction is called the ultraviolet catastrophe. Okay, this is the difference between a wood fire and also the effective temperature of the sun, where you can see that the peak is actually shifted to the right when you plot the intensity against wavelength. When you plot the intensity against wavelength, it shifted to the right, and most of the peak at the very hot temperature will be visible compared to the 2000 Kelvin. Okay. So Maxwell Planks reproduced the experimental curve. Okay, so he tried to reproduce the experimental curve by assuming that the radiation. So this is actually a physicist, Maxwell Planck. Okay, the energy for light, okay, comes in a quantized energy package, which means it will have NHF. Okay, will be based on the number of energy packets. Okay, H is the Planck's constant, which is this one. Okay, 6.63 10 power of negative 34 joule second, and also frequency. Okay, so and this energy will be based on the frequency. Okay, the higher the frequency, the higher the energy quantized. All right, so this is the solar radiation spectrum, where you can see the radiation spectrum based on the solar energy. Okay, where you can see it's also similar to what we learned, where you can have a UV, a visible, and also infrared regions. Okay, so this is the photoelectric effects and the particle theory of light, suggested by Einstein. Okay, so the Einstein get his Nobel Prize, his physics Nobel Prize, using this photoelectric effect. So what is photoelectric effect? It comes with the word photo and electric. So means photo means light, electric means electrics. Okay, so the energy of a photon. So and Einstein suggested that light comes in a bundle of energy called photons. Okay, bundle of energy. So meaning that Einstein suggested uh, light is like a particle. The light is like a particle, and this particle, okay, will obey the Planck's hypothesis, which the Planck hypothesis is E equals to hf, which whereby h is the Planck's constant and f is the frequency, and the unit for the energy of photon is joule. Okay, so when you have this energy, okay, so he tried to do some observation or try to some calculations using the experiment of photoelectric effect, which means he wants to obtain this kind of equation K max equals to E minus with work function. This is the work function, and it is not a work. Okay, it's not a work, it is a energy. This one is energy, and this one is also energy, but this one is kinetic energy maximum. Okay, so how can photoelectric effects occur? So the photoelectric effect is with the incoming light that comes with the bundle of packets hf hf hf, and try to hit the emitter. Emitter is a metal. Okay, metal with the uh, metal with the structure of atom that have electron on the outside, orbiting electron on the outside. So this energy light, okay, try to strike this electron, and then when this electron break, and it will accelerate it to the collector. So electron will be uh, captured by the collector, and the collector will give current to this. So that's how they get photoelectric effects. So from lights, okay, hit the with the proper energy, okay, to get the heat of to strike the electron, and the electron will be ejected and then will be accelerated to the collector. Okay, so the work function, okay, is normally in the electron volts, right? So the work function is E. So KE equals to E minus W naught. So W naught, sometimes they will use E minus E naught. Okay, E naught is what? HF naught. Okay, so F naught is cut off frequency, because E is also HF. So what is F? What is F naught? F is the incoming frequency, and F naught is the cutoff frequency. And F must be equal or greater than F naught in order to eject electron. Okay, and of course, this is how they did in the examples. Okay, so we will continue this chapter tomorrow, inshallah, during your lectures. Right, so I think that's all for today. Okay, please spare your questions for tomorrow, because we don't have much time right now. So I think I'll stop here. Thank you for your attention, and Assalamualaikum.